Today we will study how do we introduce shear deformation effect in the stiffness matrix formulations. So far we have assumed that our members are predominantly undergoing bending phenomena. Today we will introduce one more complication in our formulations of the direct stiffness approach, and that is the inclusion of the shear deformation effect. Now, what is the shear deformation effect? In general, when we have thin sections mean that the L by D ratio is typically larger than 10. In that case, the dominant mode of deformation is bending. So we have the bending phenomena, and this leads to deformation, and the strain energy is mainly stored in this mode. So this phenomena is predominant in the case of beams and frames. However, if the beam is very deep, say the L by D ratio is less than 6, then another phenomena contributes to deformation, and that is the shear mode. So in general, the relative contribution of the bending and shear modes can be seen from this graph. So what we can see is that when the L by D ratio is greater than 10, then predominantly 95% of the contribution for deflection comes from flexure, and this is there in the case of beams and frames which have L by D ratios greater than 10. However, when the L by D ratio is typically less than 2, then the contribution of the shear deformation is as high as 50%. So in general, the thumb rule is that when we have the sections which have L by D ratios less than or equal to 6, then we must include shear deformation effects. And these kind of sections are encountered in the case of shear walls, lift course, and general deep beams. So in all such cases, we need to include shear deformation effects. So far, our formulations have not included any shear deformation effects. We assume that the predominant mode of strain energy shall be bending, which is true in the case of beams and frames, or in axial mode, which is true in the case of truss members. So how do we include the shear deformation effect? Let's see that. So we assume that our treatment is restricted to prismatic sections only. In the case of non-prismatic sections, we have already seen how we incorporate the effect. However, for the shear deformation case, we assume that our sections are prismatic in nature. Now, in any deformed structural member, basically the strain energy is made up of a number of components such as axial deformation, bending mode, torsion mode, and shear mode. The most generalized form of the expression for strain energy is this. That is, we do a volume integration of half into stress into strain, and this stress and strain could be of any type. It could be axial stress and strain, or could be the bending stress and strain, or could be shear and torsion. So if we split this equation into various components, we'll have the components such as the bending component, which is relevant to the beams and frames. We have the axial component, which is relevant for truss members. We have torsion component, and we also have shear component. Now in the case of shear, there is one extra term which is S. So this is called as the shear correction factor or shear deformation coefficient or form factor, and is required to take care of the implicit assumptions for shear. Now what is this correction and why it is needed? Let's see in detail. Basically, in all the computations of the strain energy involving shear, we assume that the shear stress is uniform. But the actual case is that shear stresses are not uniform. In a rectangular section, for example, the shear stress distribution is parabolic in nature. So shear correction factor is introduced so that we can convert the non-uniform shear stresses into some kind of average uniform shear stress, and by including this factor, we would get same result as in the case of the actual stress distribution. So to express in mathematical terms that the equivalent shear stress is obtained from the average shear stress, that is total shear force to the total area of the section by V by A, and this is multiplied by this correction factor S, and this correction factor can also be viewed in another form, that basically the correction factor gives us effective shear area. So we have the gross shear area, and when we divide the gross shear area by the shear correction factor, we get the effective shear area. So here this factor S is typically greater than 1. So we define shear correction factor as the ratio of the gross area of the section to the effective area of the section which contributes to shear. And shear correction factor is also called as form factor. So we define it in this manner, so that's why it's greater than 1. So shear area of the particular member is that area which is effective in resisting the shear forces. In the case of I sections, for example, the web area is more effective in resisting the shear, and the flange areas, they have negligible contributions. Now, how do we mathematically define shear correction factor or the form factor? Before we go to the definition, let's just revise the basics. So in general, if we have a cross section where shear force is acting, the expression for shear stress is given by VQ divided by IB. So what is I? I is the second moment of inertia, and B is the width of the section at point we are determining the shear stress. Q is basically the first moment of the area above the plane considered with respect to the neutral axis. So Qy is given by this expression, and this is the first moment of the part of the cross section above the section or the plane considered. Now for the shear correction factor, we have this expression, and this expression we have taken directly from the solid mechanics. We are not deriving it. Basically our course is more focused on analysis part. You will go through the derivation in your solid mechanics course. So it is given by this expression. So here the square of the terms Q and P come. So essentially this involves that at a given arbitrary section in terms of the variable y, we have to find expression for Q, and then we have to do integration of Q by B whole square across the entire depth of the cross section. So that gives us the shear correction factor. So we can use this relationship and we can derive the values for some typical shapes. For example, for rectangular section it is 1.2, for circular sections it's 10 by 9, and for hollow circular sections it's 2. So now after this background, we can now use our already learned techniques to determine the stiffness coefficients for the case involving shear deformation. So we assume that we are dealing with a deep beam and the member is prismatic in nature. So we define two force systems, just like in the case of the non-prismatic members we had defined real and the virtual force system. So here we are defining two force systems. So we are applying a unit moment at the left end, and by definition the rotation caused here is F33, and the bending moment diagram for this case is represented by M1x. So if you use your origin at the left end, you get certain expression, but you can also use your origin at the right end, then you get a more simplified expression. As we have defined earlier, and we have the bending moment and shear force diagrams like this. So now we can apply the principle of virtual work, and by applying the principle of virtual work we can write this expression for F33. But what we can see is that we have a term involving shear deformation also. This term was not there in the previous treatment because we had assumed that our sections are thin, so shear deformation effect is negligible. But now we have to include it because it's important. So here m1x has this expression, and if you choose the origin at the right end, as we had seen in the previous slide, you can just flip through the previous slide and then your expression would be x by L if you use origin at the right end, and then it will enable you easy integration. And the shear force is constant 1 by L. Similarly, we can write expression for F63 where m2 is x by L with origin at the left end of the member. So we have got these terms, so we can similarly get F66, and then we can also get the expressions for F36. So with this we have now got the information how to obtain the flexibility coefficients for the case of shear deformation. And once we have the flexibility coefficients, we can make use of the flexibility coefficients and we can obtain the stiffness coefficients, for example K33, K66 and K63. So in the same manner we can get other stiffness coefficients also. So these stiffness coefficients, they would include the shear deformation effect, and we can use them directly for members such as lift course or shear walls. We can attempt this practice exercise that for this rectangular cross section, try to determine the value of the form factor or the shear deformation factor S, and for this T-beam where the L by D ratio is 3.33, you try to derive K36. Thank you very much. We will interact in MS Teams now.